Bonding in metals. We mentioned this idea of the Electron-Sea model earlier. Here's a more in-depth discussion of it. So in a metallic solid, each of the metal atoms donates one or more electrons to an Electron-Sea, or the pool of electrons, right? And so what we can think of it as is sodium metal is actually an arrangement of sodium ions. They all donated an electron to the pool. Sodium ions, and then they're surrounded by this negatively charged sea of electrons. And so they're attracted. The positive ions are attracted to all these electrons around them. Okay, and I mentioned earlier it's a little like a neighborhood, and every house sends a kid out to play, and then we're all kind of interested in staying around and keeping track of this herd of children running around like hooligans. This idea of how metals bond explains some of their properties. Metals are conductive. They conduct electricity, which is why we use them for wires, right? How do they conduct electricity? Well, the electrons in that Electron-Sea are free to move. So in this illustration here, we've kind of got this, it almost looks like a gel-like bubble around here. But there's free electrons in here, and they can move from one side of the metal to the other. When one electron moves over, another one comes in and takes its place. Those electrons are no longer tied to the specific atom that they came from, so they can conduct electricity. Two other properties of metals are malleability and ductility. You can hammer them into sheets, you can draw them into wires. You take a piece of metal and you hit it real hard with a hammer, and you might dent it, but it's not going to shatter like glass or like a brittle ionic compound would. And the reason is that these interactions, these attractions are not unidirectional. They're in all directions, and they're not localized between two of the atoms. And so if some of the atoms move a little bit, it doesn't disturb the whole bonding structure. There's flexibility in there. And then little blurb at the end of the chapter, which I won't test you on, but I think is very interesting and applicable. The structure of ozone. Oxygen is O2. That has a double bond. Ozone, O3, has weaker bonds that are intermediate between single and double bonds. It has a resonance structure. So we got oxygen, oxygen, oxygen. There's 18 electrons. 2, 4, 6, 8. Not there. 10, 12, 14, 16, 18. And there's a resonance structure for this where the double bond is over here. And so in ozone, each of these bonds is actually like a 1.5 bond. That's weaker than the double bond in oxygen. I'll draw oxygen up here. Oxygen has a full-on double bond. So here's an illustration of the planet. We have ultraviolet light coming in from the sun. Ultraviolet light is higher in energy than the visible light. And as it comes in here, we have this ozone layer. The UV light has enough energy to break the bonds in ozone. It does not have enough energy to break the bonds in oxygen. So these UV photons come in, and the ozone absorbs them, breaks into oxygen, the molecule, and free oxygen atoms. So these free oxygen atoms do not have an octet of electrons. They're not stable. And so they're going to find each other and find the oxygen, and they're going to combine and reform the ozone. And so this ozone acts as a filter for us to get rid of some of the ultraviolet radiation that comes in.